Okay, welcome everyone to section 3.1. This is derivative formulas for powers and polynomials. We look a little bit different today because I'm visiting my parents for the 4th of July weekend, and I forgot my computer charger. So I'm using my mom's setup today. She's also a math teacher, and her writing pad is quite drastically different than mine, so I apologize in advance for my handwriting today. I promise it is only for this lecture and not for any others. Alright, so in chapter 2 we talked a lot about what a derivative is and how to approximate it, but now we're actually going to start to learn how to calculate derivatives. Okay, so first we'll start with constant functions. So if we have a function f of x, which is equal to k being a constant, okay, this describing, again I apologize, a horizontal line at y is equal to k, then, up higher, then we have f prime of x is equal to 0. So in this case, our derivative is 0. Our derivative is always going to be 0. And if we think about this, it makes sense because if we have a set of axes here and we have our function here, y is equal to k, if our derivative is the slope of the tangent line, at any point we pick along this function, our tangent line is going to be horizontal. So we are going to have a derivative of 0, a slope of 0. Alright, so the derivative of a constant function is always going to be 0. Next, we can look at linear functions. So we already know, I'll see if I can write this. I'm going to try to do minimal writing today, just a lot more talking. So we already know that the slope of a line is constant. So slope of a line is constant. Okay? This tells us that the derivative of a linear function should be constant. So come down here, lower, derivative of a linear function should be constant as well, right? So, where am I writing? If we have the function f of x is equal to mx plus b, right? This is a linear function. Then f prime of x should be our slope, m, which is a constant. Alright, next we have our constant multiple rule, where if we're taking the derivative, so the derivative with respect to x of a constant c multiplied by our function f of x, this is the same thing as taking our constant c and multiplying it by the derivative of our function f of x. And right, this is in Leibniz notation, and if we wanted to write it in function notation, it would just be c times f prime. Okay? So these are all equivalent statements. Basically, this is saying derivatives don't care about constants. They can come in and out. Okay? Because they have nothing to do with the value that we are taking the derivative over, which is x, right? Our constant has nothing to do with x. Okay? So then we have our sum and difference rules. If I can find my cursor. Our sum and difference rules. So if we have, the derivative with respect to x of f of x plus g of x, all right, that's the same thing as saying the derivative of f of x plus the derivative of g of x. All right, so we can distribute derivatives into an addition, okay? Then, or in a summation. If we have a derivative of a difference, so of f of x minus g of x, we can do the same thing. So it's the derivative of f of x minus the derivative of g of x. Alright, so we can distribute the derivative into addition and subtraction. Okay? Now we're ready to learn the power rule. So the power rule is our first official way of calculating a derivative. Alright? So let's see if I can bring my cursor to a starting place here. Okay, down here is where we are. I can't tell where my cursor is if you can't tell why I'm writing like a crazy person. Alright, so we have d dx of x to some power n. Okay, if we're trying to take this derivative of x to some power, the way we calculate this derivative is we pull the exponent down, make it a coefficient, so now we have n times. Then we need the base still, x. And then the power is going to be the exponent it was raised to minus 1. Alright? So this is our first official derivative calculating rule or formula. This is called the power rule. Alright? And we're going to have a ton of practice with this in our first example. So our first example asks us to find the derivative of the following functions. So here our first one is f of x is equal to 125. Alright, so what do we know about 125? 125 is a constant. So we know that the derivative of a constant must be 0. So f prime of x, which is the derivative with respect to x of 125, but there is no x, alright? So this is just 0. The derivative of a constant is 0. Okay? Over here we have f of x is equal to 19 times x. So f prime of x, well, this is the derivative with respect to x of 19x. Okay? So this is a linear function. Linear function with an intercept equal to 0, right? If we had y is equal to mx plus b, we're adding plus 0 here. Okay? So our linear function with b is equal to 0. So we know that our derivative of a linear function must be the slope. And here the slope is 19. So we could just up and say, well, this is equal to 19. But I'm also going to show you why that's true based on the power rule. So our constant multiple rule says that we can pull this 19 out front and say that this is the same thing as 19 times the derivative of x with respect to x. Okay, so if we then used the power rule, all right, and said this is raised to the first power here, okay, that's a 1, and that's just always a given, right? We just don't write x to the first power. X by itself is x to the first power. So if we use the power rule, we're going to have 19, okay? I'm going to keep our other work here in a bracket. So we'd bring down our exponent, multiply it by x, and then we raise the x to the 1 minus 1. Okay? So this is the same thing as 19 times 1x, which is just x to the 0th power, and anything to the 0th power is just 1. So this is 19 times 1, which is 19. So our derivative of 19x is just 19. Okay? Let's keep going with example C. So we need f prime, this time of t. So this is going to be d dt of 2 minus 6t. All right, well, we have a difference here. So we can go ahead and use our difference rule and split the difference. So we have the derivative with respect to t of 2 minus the derivative with respect to t of 6t. Okay? Well, our first term, the derivative of 2 is just a constant. So we don't need, or 2 is just a constant, so the derivative of a constant is 0. All right? Then we have the derivative of 6t. Well, our constant multiple rule says we can pull 6 out, and then we just have the derivative with respect to t of t. All right, well, down here, this is the exact same thing that we did a minute ago with the derivative of x with respect to x. We did the power rule, we got x to the 0th power, which was 1. So that exact same thing is going to happen here, and we'll just end up with negative 6 times 1, which is just negative 6. Okay? So our derivative of 2 minus 6t is negative 6. Now let's look at the derivative of 1 over x cubed. Well, first, we don't know how to handle any fractions yet. We didn't talk about any kind of division rule or anything like that. So how can we rewrite this to use the only rule that we've learned so far, the power rule? Well, we can bring the x cubed up to the numerator, and all we have to do is negate the exponent. All right, so 1 over x cubed is the same thing as x to the negative 3. So now we can use the power rule. So f prime of x is our derivative with respect to x of x to the negative 3. So we're going to use the power rule here. All right, so we have negative 3 coming down out front, multiplied by x, raised to the power, the original negative 3, minus 1. Okay? So this will give us negative 3 times x. Negative 3 minus 1 is negative 4. We can rewrite this one more time and make this negative 3 over x to the 4th. All right, if we move the x to the negative 4 down, we negate the exponent, and so it ends up being positive on the denominator. Okay. Looking at part E, we have f prime of x is equal to the derivative of 3 square root of x. Well, how can we rewrite this? Let's see. First of all, we can pull the 3 out front because of our constant multiple rule. So 3 times the derivative of the square root of x. We can rewrite this as x to the 1/2. Okay? The square root of x is the same thing as x to the 1/2. So now we can go ahead and use our power rule and say we have 3 times, I'm going to leave our other work here in brackets so that we don't get lost in the multiplication afterwards. So we're going to bring down the 1/2, multiply it by x, and then we have 1/2 minus 1 in our exponent. Okay? So we still have 3 times 1/2. X to the 1/2 minus 1, well, that leaves us with negative 1/2. Okay? We could come over here and simplify this a bit. Now we have 3/2 x to the negative 1/2. If we want to make that exponent positive, we can move, whoa, that's not what I wanted to do. Okay, where is my mouse? Okay, so we can have 3 on the numerator, 2 times x to the positive 1/2 on our denominator, which we know that x to the 1/2 is the same thing as the square root of x. So we have now found our derivative. For 3 times the square root of x, we get 3/2 of 1 over the square root of x. Okay. And our last part for this example, we have a polynomial. Alright, so it's just a series of derivatives, okay? So we're just going to say that f prime of x, well, it's the derivative of everything that we have so far. So we have the cubed root of x plus 1 over x squared minus 5x. Keep pressing buttons on the pen, I apologize. Okay, so we're just going to use a combination of the sum and difference rules to split this into 3 different derivatives to simplify it for us. So now we have the derivative with respect to x of the cubed root of x plus the derivative with respect to x of 1 over x squared minus the derivative with respect to x of 5x. Alright, so now it's in bite-sized pieces. We can handle this a little bit easier. How can we rewrite the cubed root of x so that we can use the only rule we know, which is the power rule? Well, we said that the square root of x was the same thing as x to the 1/2. So the cubed root of x is the same thing as x to the 1/3. Okay? Next, we have the derivative with respect to x of 1 over x squared. Again, we want to use the power rule, so we're going to make this x to the negative 2. We're just rewriting it. We're not changing the value whatsoever. And then we can use our constant multiple rule to say that this is the same thing as 5 times the derivative of x. Okay? I've got to be around here somewhere. Oh, there I am. Okay, so let's go ahead and calculate these derivatives. So we're going to take the exponent, bring it out front, so we have 1/3 times x, and then we have 1/3 minus 1 in our exponent. Then we're going to add our next derivative, so we'll pull down the negative 2. Remember to take the sign with it, okay? So negative 2 times x, raised to the negative 2 minus 1. And then we have minus 5 times the derivative of x, which we've already done now twice, we know is just 1. Alright, I'll write it like this for completeness, but we don't ever need to write multiply by 1, right? Alright, so let's clean this up a little bit. We have 1/3 x. 1/3 minus 1 gives us a negative 2/3. See, can I come back down? I don't know where I am. Oh, there we go. Negative 2/3. Okay. Then we have minus 2 times x raised to the negative 2 minus 1, which is negative 3, and then minus 5. Alright? And we could go ahead and move our exponents down to our denominator if we wanted to make them positive, but in the interest of time and space, we're just going to leave this here and say we have officially finished calculating all of the derivatives. Okay? So we found the derivative of our original polynomial. So now in example 2, we're going to use these derivative skills to find the equation of a tangent line. So we've talked a lot about tangent lines, and we've talked a lot about how the derivative of a function is the slope of a tangent line. So now that we know how to calculate the derivative, we can go ahead and find the equation of a tangent line. So the first thing that we need to do is find the derivative. Okay? So we need to calculate f prime of x. Well, this here is just a polynomial. We have the derivative of x cubed plus 2x squared minus 5x plus 7. Alright? We just did an example where we calculated the derivative of a polynomial. Okay? So we can go ahead and break this up into pieces. And if you've already got the hang of this and you're thinking you could break this up in your head and skip a few steps, that is okay. However, I do encourage you to write down all of the steps because soon we'll be doing a bit more complicated work, and it's really easy to lose a negative or lose a constant somewhere if we're skipping steps. Alright? So we've now broken this down into 4 separate smaller derivatives for us to handle. Alright? So we have the derivative of x cubed. Well, this is going to be 3 times x raised to the 3 minus 1, which is 2. Okay? Then we have a constant multiple rule here, so we want to go ahead and pull this 2 out. And then I know that we'll be left with the derivative of x squared. So, if we just think about the derivative of x squared, we're going to need to pull the exponent down, multiply by x, raised to the 2 minus 1, which is just 1. So we can leave it like this. Next comes the derivative of a linear piece. We just have 5 times x to the first power. That's when it's linear. And we know that our derivative must be constant. It's going to be the slope of this little piece here, 5x. We also know that if we use the power rule, we'll end up with x to the 0th power, which is just 1. So we know that our derivative of 5x is just 5. And lastly, we have the derivative of 7. 7 is a constant, and the derivative of any constant is 0. Alright, so we don't need to write the plus 0, but I'm doing it for completeness. Alright, let's go ahead and drop these brackets here. So we have 3x squared plus 4x minus 5, and this is our derivative. Sorry, I got ahead of myself in my notes here. There we go. This is our derivative, f prime of x. Okay, so I told you we were going to calculate the slope of the tangent line so that we could find the equation of the tangent line. And you might be thinking, all right, we calculated the derivative. How on earth does this polynomial give us a slope? All right, well, the next thing we need to do, we need to evaluate at the given point. All right, it's a very important key piece. Pretend I crossed that T over there, okay? I don't know where my pen went. So, we need to evaluate our function, our derivative function, f prime of x at x is equal to 1. So f prime of 1. So we're going to plug 1 in everywhere we see an x. So we have 3 times 1 squared plus 4 times 1 minus 5. This is going to give us 3 times, or 1 squared is 1, times 3 is 1. Again, I said the wrong thing. Is 3 plus 4 times 1 is 4 minus 5. So we have 7 minus 5, which gives us 2. And this is our slope at x is equal to 1. Alright, so we're looking for an equation of a line, which we know is y is equal to mx plus b. Alright, we also have another form, so this is called the slope-intercept form, where we have m is the slope and b is the y-intercept. Alright, and we also have y minus y1 is equal to m times x minus x1, where this is called point slope form. So m is again the slope, and we have a point x1 comma y1, which are these values here. Okay, so we need a point in order to be able to use our point slope form. We already know that x is equal to 1 is on our graph. Alright, so bring this down. X equals 1 must be on our graph somewhere. So we need to find the corresponding y value. And how do we do this? Well, the y values are given by the original function, f of x. So if we plug in x is equal to 1 into our original function, we're going to get our corresponding y value. So we have y is equal to the original function evaluated at 1, which is going to be 1 cubed plus 2 times 1 squared minus 5 times 1 plus 7. Alright, so this comes out to be 5. So we have our point 1 and 5. So this is our x1, y1. We have our slope is 2. So the equation of a tangent line is going to be y minus 5 is equal to 2 times x minus 1. And if I can give myself a little bit more space right here, then we can simplify this. Let's see, where's my pen? Here it is. So we can go ahead and distribute the 2 over here on the right-hand side. So we have y minus 5 is equal to 2x minus 2. And then we can add 5 to both sides. So we get y is equal to 2x minus 2 plus 5. So we get y is equal to 2x plus 3 is our equation of the tangent line at x is equal to 1. Alright, so that was our first pretty hefty problem. We have just now calculated the equation of a tangent line. We did this by calculating the derivative, evaluating the derivative at the point that we cared about, which was x is equal to 1, and then we had to find the corresponding y value for our x value. Okay, we did that by plugging 1 back into our original function, and then we use point slope form to find the equation of the line. Alright, so hopefully you feel pretty accomplished. Now we're going to move on to example 3, which is bringing us back to the discussion of revenue. Alright, so we're given a revenue function, which is r of q is equal to 1000q minus 3q squared. We are to find and interpret r of 125 and r prime of 125. Okay, so r of 125, we've done something like this already 100 times. We just need to plug 125 into our original equation. Okay, so we're going to end up with 1000 times 125 minus 3 times 125 squared. Alright, which comes out to be equal to 78,125. So now we're supposed to interpret this. Okay, so let's see, what are we plugging in here? Where's my mouse? Over here. Okay, so we are plugging in q is equal to 125. And what is q telling us? Well, this is the number of units, whatever this company is producing, produced. Right? So our revenue function, we know, is always going to be in dollars, and it's going to be the amount of money that is accrued by making these number of units. So this is the money gained from making number of units. So our total interpretation here is producing 125 units is going to bring a revenue of $78,125. Okay? So the next thing we need to do is calculate r prime of 125. So the first thing we need to do for that is find r prime, just of q, right? So this is going to be the derivative with respect to q of the function 1000q minus 3q squared. Alright, so we can use our difference rule. We get the derivative with respect to q of 1000q minus the derivative with respect to q of 3 times q squared. Alright, so then we have a constant multiple rule where we can pull out the 1000, and then we just have the derivative of q with respect to q, which is similar to what we've done before. It's just 1. Alright, then again we can pull the 3 out front because it's a constant multiple, and then we're going to be left with the derivative of q squared. So we'll pull down the 2 times q to the 2 minus 1, which is just 1. Alright, so Our derivative is 1,000 minus 6q. This is our derivative of the revenue function. So now we're asked to evaluate the derivative at 125. So the derivative at 125 is 1,000 minus 6 times 125, which gives us 250. Alright, again, to limit the writing here, let's see, I'm just going to make a note that this is the marginal revenue, which we talked about in the last chapter, right? The marginal revenue. So, and I'll just say that this is the revenue, so the revenue will increase by this $250 per unit after making the 125 units. So that's our interpretation of r prime of 125. Alright. Then I have room to make a little note down here, so we're going to note, where's my pen? Note, okay, that the derivative of position, is velocity, okay, and then the derivative of velocity is acceleration. Alright, so this tells us that the second derivative of position is our acceleration. And we make note of this because we need this fact in example 5. Alright, so this is our last example, and then we're going to wrap up today. So if my pen will cooperate, okay, sure, we're over here. So we have the height of a grapefruit that has been thrown into the air is given by this function, f of t is equal to negative 4.9 t squared plus 25t plus 7. And we are to find the velocity of the grapefruit at t is equal to 2. Well, we just made a little note that said velocity is the derivative of position. So we need to go ahead and take the derivative of this height function. So this is going to be the derivative with respect to t of our function, so negative 4.9 t squared plus the derivative with respect to t. I'm going ahead and breaking up the differences and additions here, so 25t plus the derivative with respect to t of 7. Okay? So, the derivative of negative 4.9 times t squared, we have a constant multiple rule taking effect here, so negative 4.9. Then we'll be left with the derivative of t squared, which is going to be 2t. Okay? Then we have the derivative of 25t. Again, this is one of those linear terms where our derivative is just going to be the constant, 25. And then we have the derivative of a constant, which we know is always going to be 0. So, our derivative, f prime of t, is going to be negative 4.9 times 2t. I actually meant to go ahead and do that calculation. Alright, let's see if I can bring my pen back. Here we go. We have negative 9.8 t plus 25. Alright, so this is our velocity function, our first derivative. But we were asked to find the velocity at a specific time, at t is equal to 2. So we need to go ahead and plug this in to our velocity function and get 9.8 times 2 plus 25, which evaluates to be 5.4. Alright, so we've now found our velocity at t is equal to 2. And lastly, we need to find the acceleration of the grapefruit at t is equal to 2. So our acceleration is our second derivative of position, which is our derivative of velocity. So, here's the pen. Here we go. So, our acceleration function, we need our second derivative, which is our derivative with respect to t of our first derivative, which we found to be negative 9.8 t plus 25. Okay, so if we go ahead and split this into two different derivatives, we have the derivative of negative 9.8 t plus the derivative of 25. Where's the pen? Nope. There we go. Alright, equals. So we have a constant multiple here. We can pull out the negative 9.8, and then we'd be left with the derivative of t with respect to t, which again we've done several times. It's just going to be 1. Okay, so times 1. And then we have the derivative of 25, which again, 25 is a constant. So the derivative of a constant is 0. So our second derivative, which is our acceleration, is negative 9.8. This is our acceleration. Alright, but again, we were told to find the acceleration at t is equal to 2. So we have our acceleration at 2. Well, there is nowhere to plug in a t. It's a constant function. So it doesn't matter at what time, our acceleration is always going to be negative 9.8. Okay? So with that, I will leave you with section 3.1. Don't forget to take the comprehension quiz, and I'll see you in section 3.2.